Hi, welcome back. Today we're studying a new piece of physics, still working in the waves chapter. We know that waves are disturbances caused by the vibration of particles. We also know that if you have two identical waves crossing over each other, they can interfere, and with a combination of constructive and destructive interference, produce something called a standing wave. Today we're looking at a new piece of physics called diffraction. Diffraction is less about the waves moving through the medium and more about what else is there. In other words, boundaries, barriers, things in the way. If waves, such as sound waves, hit the edge of a boundary, unlike particles, they don't just either hit it and stop or not. They bend. They'll move around the corner so that, kind of like in this cartoon here, depending on where you are behind a house, you could clearly hear somebody speaking or shouting in front of it. Those sound waves kind of wrap around that barrier. Again, this is a thing that waves do that particles don't. This is a way that our new physics is different from the physics we've done prior. Here's a nice picture showing this effect in terms of water waves in the ocean. This is actually right from Google Earth. You can see that there's these barriers built out in front to kind of protect the beaches from the ocean. And look what's happened between them. There's these gaps. And in each gap, the linear wave fronts that are approaching from the open ocean are bending around and making these kind of circular things that are coming inward. You can actually see some of them in the satellite photo. And in fact, if you look at the shape of the shoreline, you can see that they've actually moved the Earth around and shifted it in response. So these diffraction effects behind the barriers are what produces these semicircular wave patterns behind that barrier. Let's look a little more closely at that. So this all depends on two things: the size of the waves, or its wavelength, and the size of the barrier. So for the first example, we have a small opening, much smaller than the wavelength, and you can see, just like in the Google Earth image, this semicircular pattern radiating outward, lots and lots and lots of diffraction bending out and around that corner. The second example shows an opening that's much larger than the wavelength of the wave themselves, and there's minimal diffraction there. You can still see a little bending at the corners if you look closely, but typically you'll just see these wave fronts passing through mostly unaffected because that opening is much bigger than the waves themselves. You can also flip this around, and instead of thinking of a hole in a large barrier, you can think of a small barrier in an open ocean or open medium. And so it's all kind of reversed in that case. If the barrier is much larger than the wavelength, then you can see some diffraction effects curling those waves in. And if you look from far enough away, they'll wrap into enough to fill in around. But there'll be a shadow cast behind it. On the other end of it, if the barrier is much smaller than the wavelength, then it's almost like there's no barrier there at all. The diffraction effect is so large that the waves just pass over that barrier as if it wasn't there. Here, let's look at another cartoon example of this. So you have two objects, the ship at anchor and the chain itself going into the ocean. The same set of waves is passing across both. So you can see from the large-scale picture that the waves, there's a calm area behind the boat because the boat itself is much bigger than the waves, the length of the waves, then it's basically going to cast that shadow, and you'll have minimal wave action right behind it, although you can see it sort of curling in behind it over time. By contrast, if you zoom in close and look at that chain, well, a chain isn't going to stop waves, is it? So those waves are just going to pass right around it as if it isn't even there, because diffraction allows it to do so. Another neat example is light. Light is, of course, a wave, and light can diffract. But since the amount of diffraction depends on the wavelength, we don't often see this. Think about it. If you're standing in your room speaking, somebody in the hallway could clearly hear your voice, and that's because the wavelength of sound is roughly the same size as a door. So there'll be lots of diffraction, and the voice sound waves will bend around the corner and allow you to be heard. But they can't see you, can they? You can't see around corners because the wavelength of light is much, much, much smaller. It's on the order of hundreds of nanometers, which is pretty itty-bitty. But if you make very, very small holes and shine light through, you can see diffractive effects. So with this picture, not only can we see that the light is bending, but the amount of diffraction bends on the wavelength, which we haven't studied this yet, but that means color. So you can see that the red light passing through these pinholes is bending more than the yellow, green, and blue light, as it's shifting further off from the holes themselves. As a wrap-up question, let's think again about standing waves. If you have standing waves being observed in water, would they be most often produced by periodic waves being absorbed at the boundary with a new medium, refracting at a boundary with a new medium, diffracting around a barrier, or reflecting from a barrier? Pause for a moment. Think about that. If you answered 4, good on you, because 4 is the correct answer. A reflection from a barrier would produce a periodic wave of the same frequency and amplitude. And when those reflected waves pass through the original waves, you would see that constructive and destructive interference producing a standing wave effect. Thanks for checking in on some physics today. I'll see you next time.